April 11 or 411, 2023, Seattle, Washington. Sunny, windy, sustained wind, gusts. Weather reports have that there's spotty and heavy rains in the uplands, and out of the coast is clear and calm. Today I thought I'd read some more about the differential equations. There's been, in the previous talk about the differential, there was some idea of how to bring together these elements of topology and elements of algebraic geometry and elements of this differential geometry, and then discussions about methods of solutions about the closed forms, and then this differential geometry is getting into its submersions or linearizations, that it works up in terms of these systems as about these submersions or immersions of the differential geometry, and how they're to work out closed forms that make solutions in finite terms. And these and then for topology, the sheaves, where one great thing about topology is both its absolute opinion about measure and as of the continuous, and then also the the quasi-invariant for measure theory, when we have three definitions of continuity: this line continuity, signal continuity, and for our standard real field continuity. That what I thought I would look into was some more about the differential equations and the ordinary differential equations. And before I'd been thinking of them in terms of the linear and the applied, but then there's the notion of them in terms of the univariate and applied, and about what gets into all the manners of solutions, and kind of as Stefani indicated in the talk before when reading some of this about the systems with the symmetries, about the toolkit of the basic and the extended toolkit of the solutions of differential equations, that there's how to get figured that there's these ideas that for this and not necessarily a unification effort of sorts, but in a sense a unification effort in terms of the schools of the fields and subfields of the analysis that goes on into the establishment of these things like populations and the systems of balance and equilibrium and chemical reactions and economics and all this stuff, which was described as factors of the applied. That in this manner there'll be some more working into what are these descriptions of the fundamentals of the differential analysis, and then also how it's possible to result that then we can bring what are some of the methods of the ancients that are underserved these days, that after we've arrived at this general milieu of real analysis, and we point at Bernard Riemann and our fundamental theorems of calculus, and then as how it so results in this theory of functions, and everything is pretty much in Descartes' coordinates, the functions of things, how it gets so to then is figure out what's in terms of like these orbifolds or orbital manifolds, what I've been reading about, and then also in terms of these how you would say these underserved methods of the toolkits that have simply been gathering dust in David Hilbert's old Infinite Living Museum of Mathematics, that then it's possible to work up this notion of this submersions and sheaves and symmetries, as was in the previous talk, how then they can arrive at kind of a corralling, a bringing together in terms of the sides of the fence, the various notions that together will help provide a bit more of a heuristic, a bit more of a holistic approach to differential equations. Now, this isn't really my study or field, this subfield of mathematics. I mostly have been studying the continuous and the foundations, as it were. But at the same time, after having a formalism of real analysis, it it's arrived at that all such things in terms of the applied for the analyst really are in this realm of the differential equations. And such methods as finite element analysis, and then after this differential geometry, and such methods as the setups. For example, these ideas of all these different setups that work up for the nonlinear contributions. It's funny that the book is called Contributions, but it's about contributions, about these numerical methods and the partial terms and the whole terms. So then it's about getting into some more ideas about how to encapsulate in what's a learning or a sort of a course, what could result something that would make for then an ontology of a phylogeny for cladistics as a catalog of a dictionary, of an encyclopedia of the world of differential equations, and then what other mathematical systems and setups arrive at being same solutions. And as it's kind of put in some point where, oh, well, every differential equation is assumed to have solutions. And so when those become real numbers and it's possible to determine what are the outlying extents of the outer products for this, what results really this inner product, the solutions, that it's so arrived at then for these systems of solutions from these superpositions of states or these under constrained systems that have, according to then conditions and of boundaries and values, back into these talks about the continuity laws and all this kind of thing, how it's so arrived at introductions to the trails in the field that lead to all these sorts necessitated formalisms and symbolisms and constructs that can be shared and can be tractable and sensible and fungible for everybody. Also how to build the intuitive and build the intuition so that it arrives at that people of usual sorts can approach this very, very, very complicated field and have some idea of where to look and how to look for under which reflections will provide context for a completion and continuation of the gain of these things. So today I stopped by the bookstore as is my usual want, and I walked around and I was looking through it, and I found another one of these textbooks from the University Mathematical Texts. So what these are university mathematical texts, and this one's first edition was like in 1939 or something like that. So in 1943, after 1939, the author has written this preface. He says, the object of this book is to provide in a compact form an account of the methods of integrating explicitly the commoner types of ordinary differential equation, and in particular those equations that arise from problems in geometry and applied mathematics. It takes the existence of solutions for granted. The reader who desires to look into the theoretical background of the methods here outlined will find what he seeks in my larger treatise, Ordinary Differential Equations. With this qualification, it will be found to contain all the material needed by students in our universities who do not specialize in differential equations, as well as by students of mathematical physics and technology. As one of the first things a beginner has to learn is to identify the type to which a given equation belongs, the equations for solution have not been printed after the sections to which they refer, but have been collected at the end of the book. When the contents of the first chapter has been mastered, the reader may test his skill by attacking examples selected at random from numbers 1 to 122, and similarly for the later chapters. The examples occur roughly in the order of the table of contents, so that working material is always available as reading progresses. Now, one thing to make in contrast to what the author has noted here is that there's the identifying the type of solution to which an equation belongs, but there's identifying an equation which belongs to a setup. And so this is where sometimes when trying to analyze what would be a dynamical modeling, that our dynamical systems and dynamical modeling is all of analysis. So all of analysis is called dynamical modeling in dynamical systems. so the idea of what formula to write, giving things terms and then just writing out an abstract formula that this is the adding up all together is what a way to start is. And then finding systems of equations that are kind of tractable and known as after that, in a sense. This is that otherwise, when the equations are provided, solve these equations, that's after there's already the analysis of this is for our model fitting, this is for our models, this is for the things that it could be. For example, a very comprehensive and thorough statistical analysis of things in model fitting, where given an unknown distribution, it's matched to all the 20 plus known usual distributions by shape and scale. And then working up into clustering and means and this kind of thing in terms of central tendencies and attenuating tendencies, that then you can arrive at some more of the context why this very complicated field then is to arrive at what makes for methods, kind of like differential geometry offers that according to this theory, then we can make up all sorts finite methods or along these lines. Or that these contributions to nonlinear partial differential equations address all kinds of problems that have specific setups and they illustrate the toolkits that they use. That then for something like that differential topology, that then it helps explain why, in accordance to these other fields, function theory, measure theory, topology, that those objects are primary in their fields, and what it means when they're represented as elementary in these other fields or theories, how it can be what is underdefined or overdefined results that it can be set up and solved. So chapter 1 is equations of the first order and degree. Chapter 2 is integral curves. Chapter 3 is equations of higher degree. Chapter 4 is equations of the second and higher orders. And chapter 5 is linear equations, and then solution in series is developed at the end. And so what I figured to do is read some of this first definitions here. Equations of the first order and degree. Definitions. Let x be an independent and y be a dependent variable. Let y prime, y double prime, dot, 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 y to the nth prime represent successive derivatives of y with respect to x. Then any relation of equality which involves at least one of these derivatives is said to be an ordinary differential equation. The term ordinary distinguishes it from a partial differential equation, which would involve two or more independent variables, a dependent variable, and the corresponding partial derivatives. So otherwise you have to figure out how to combine parameters that then you have that a parameter is more than a real number. So these are ordinary differential real equations, and they may be framed in the complex. They may have a complex variable as is the usual next sort of number. But you also can think of numbers as tuples, where the x and y together form together a parameter. And then when you fold that up in a triangle and you kind of have one line and infinitesimals and infinities on either side, and how they box up in a R3 or something like Euclidean space is a higher level operation. But the idea here is that besides the ordinary differential equations and distinguished from the partial differential equations, that they at the same time it's just a reparameterization that's described, or a deparameterization that's described, in terms of then what else is held fixed or made open. The term ordinary distinguishes it from a partial differential equation, which would involve two or more independent variables, a dependent variable, and the corresponding partial derivatives. The order of any differential equation is the order of the highest derivative involved. Now, we assume here that we're only to some finite derivative, because we start from the origin and we count numbers ever higher in an unbounded fashion, each finite, infinitely many, or an infinitude. There can be a consideration of something that's infinitely differentiable. and the family of functions C empty, like that, this family of functions are so. So that maybe we call it an infinitely differentiable, if ordinary differential equation. Thus, any relation of the form f of the variables in a comma list, in a parenthetical bracket of x comma y prime comma dot 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 comma y to the nth prime equals 0, that it's an identity that's so established. And one of these additive identities is there's been discussed the additive identity is 0 and the multiplicative annihilator is 0. That there are lots of ongoing things in regards to the algebras about the annihilator that are going on in the field of differential analysis with regards to those being a subset of all possible formulas that admit a particular forms that then have these operator calculuses up above them. Here it's just that this sequence it represents the variables that can be written in this general form, in what's some normal form. It's not necessarily the most concise form, nor necessarily the most tractable form. It just says that any one of these type of things, of this type of thing, admits this form. Is an ordinary differential equation of order n. Usually x represents a real valued variable and n represents an integer valued variable. And n usually represents a natural integer valued variable, which may be the whole integers from 1 to infinity, or when we say natural integers, 0 is included, 0 to 1, 2, 3 to infinity. Differential equations, both ordinary and partial, are of frequent occurrence in mechanics and mathematical physics, but the illustrations that best serve to introduce the subject are taken from the geometry of plane curves. Curves on a plane. That's the old definition of a classical function as a curve on a plane. It equates a relation that's 1-to-1 and onto of two variables. The classical definition of function does not have straight lines, vertical lines. It can have straight lines, horizontal lines. It doesn't have an infinite asymptote. These classical functions are all members of C to the empty and are infinitely differentiable. Not all functions are a so, and for example, a function as a circle makes it so that often the methods involve having to split it up and then figuring out what happens at the boundaries, both the rotation or as of around the path of the thing, and then also that when the boundary reflects that it's not really a boundary, it's an absence of boundary, it's a transit of a sort. The equation little f of x comma y comma c equals 0, in which x and y are rectangular coordinates and c is a parameter or arbitrary constant, represents a family of curves in which one curve corresponds to one value of c, another curve to another value. If regarding c for the moment as fixed, we differentiate with respect to x, we obtain df dx in the partial of plus df dy of y prime equals 0. Generally speaking, 1.2 will involve c. If c is eliminated between the two equations, there will result in an equation involving x, y, and y prime, say big F of x, y prime equals 0. That is an ordinary differential equation of the first order. When such an equation is polynomial in y prime, but not necessarily in x and y, the index of the highest power of y prime involved is said to be the degree of the equation. When the equation is polynomial in y prime, that's its degree. So that's order vis-a-vis degree. The degree is the order or rank of the polynomial of that when such equation of the first order there, that like so. One thing that this kind of gets to is what's called the hypergeometric. And so the hypergeometric is really quite a thing, and it gets into up and above the monomial up and above the polynomial is this hypergeometric, and a lot of recurrence relations in these things are defined about the hypergeometric. And it's also very significant in probability theory when there's any kind of multivariate analysis. The hypergeometric has got a lot going on. And I don't really know how to frame it exactly in terms of the arithmetic and the geometric of the harmonic. But it's along the lines of then that a bunch of different integer sequences, the numbers of things, so-and-so's numbers and dot, 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 or the various special functions are get quite involved in the hypergeometric as a very general way of things. Geometrically, the differential equation, just mentioned, implies that at any given chosen point of the xy plane, the derivative has a certain value or values. That is to say, it symbolizes a property of the gradient of any curve of the family 1.1 that passes through the point xy considered. This is just kind of a reflection on that these are classical functions in the old sense that as long as you draw from left to right and never lift the pencil, and that it results that is a classical function in this coordinate setting, like as of Descartes' Cartesian coordinates. Whereas in a polar function where the variable is the angle, it's a circle. So drawing a line with curves that it eventually has a line connecting any 2 points, and that there's no line perpendicular to that, which doesn't have crossing the function, that's a classical function. The equation y equals x squared plus c represents a family of equal parabolas having the y-axis as their common axis. The axis is the asymptote. It's as where the other coordinate is 0. On differentiating with respect to x, we have y prime equals 2x. This is familiar as that the derivative, a function of the function x squared, is 2x. And that the constant, the constant of that differentiation is a scalar, is a translation in that parametric form of the line, and this curve, and that it results being a 0 in the function, and so it becomes free or dislocated, unlocated in that sense. The constant integration arises whenever you take a solution in these integral curves. There's always an implicit constant added to it. The arbitrary constant c has disappeared, so that this is actually the differential equation of the family of parabolas. It expresses the fact that all the curves of the family have the same gradient at the points where they are cut by a line parallel to the y-axis, namely a gradient equal to twice the abscissa of the line. The abscissa is where it drops to the axis, the value at such point. The equation y equals constant x squared represents a family of similar parabolas having the y-axis as their common axis and all touching the x-axis at the origin. These are basically the scaling of each of those by a scalar, c, which is a non-zero real value, because the 0, 1 would be the same thing as the 0 function. That c is a parameter or arbitrary constant is all he says, but going on, the equation y equals cx squared represents a family of similar parabolas having the y-axis as their common axis and all touching the x-axis at the origin. The f0 is 0. Differentiating, we obtain y prime equals 2cx, which involves c. If this constant is eliminated, we obtain the differential equation y prime equals 2y over x. which expresses the property that any line y equals mx, the parametric form of a line, absent a constant, through the origin, or that the constant is 0, intersects all curves of the family in points where they have the same gradient to m, gradient or slope, rise over run, of the tangent curve to the curve, the tangent line to the curve, rather. So here it's interesting that he's just shown that you can frame what's a linear equation and what we would call a polynomial in the terms of the monomial and the one variable there, vis-a-vis a multinomial or what, that also can be written in this way in a differential equation. This is where all the functions that have that are a differential, when you're just computing the constant of value for a given function, that's not so also defined as parameterized by the derivative itself. It's this kind of thing. So the parabola is so written. 2. Integration. The process of elimination by which the differential equation 1.3, this is the f x y prime equals 0, was obtained from the primitive equation 1.1, which is the f x y c equals 0, is in general not reversible. The action of recovering the primitive or an equivalent expression is known as integration. More precisely, to integrate or solve a differential equation for a derivative, what's its antiderivative? More precisely, to integrate or solve a differential equation of the first order is to determine all the relations f x y equals 0 such that the values of y and y prime deduced from them in terms of x shall satisfy the differential equation identically. This is that the solution is in the form, that the solution is also in the other form. It's complement. And that basically defines the constraint that limits it, and then because in the higher order plane or is all the crossing functions, that it's only as of these unique solutions among distinct solutions. As for what is unique or distinct, just to the value to do. When an infinite set of such integrals can be grouped in one comprehensive formula involving arbitrary constants, say f x y c equals 0 or 1.1, it is known as a general integral. It is in fact either the primitive or an expression equivalent to it. He adds a footnote. General theory proves that a differential equation of the first order has one and only one distinct general integral. If two integrals exist, each of which involves an arbitrary constant, they can be transformed into one another. But there may be integrals other than those that can be obtained by assigning particular values to c. These are singular integrals. Any integral that can be obtained by assigning a definite numerical value to c is a particular integral, but there may be integrals other than those that can be obtained by assigning particular values to c. These are singular integrals. As an example, the equation y prime squared, so that we see that the term is in y prime, and then it's taken as of a higher degree or rank, minus x y prime plus y equals 0. So that there's an expression in the order of y prime squared and in the order of y prime and then y itself in terms of negative x, which is of the first order and second degree, possesses a general integral y equals cx minus c squared. These are these constants of integration or what that so arise. This represents the family of straight lines, and any particular integral corresponds to a definite line in the family, but the equation is satisfied also by y equals 1/4 x squared, which represents not a straight line but a parabola. This is a singular integral. The remainder of this chapter will be devoted to equations of the first order and first degree. That's kind of interesting. You know, when I took some courses in ODEs and PDEs and IVPs and BVPs, initial value problems, and boundary value problems, that wasn't really the formalism, and it kind of came up in Asbat later, and so it's kind of interesting to kind of figure out, and I'd like to collect my text from that and kind of contrast that with this about the preliminaries that's coming up in these definitions. But that said, these were the texts for about 30 or 40 years of usual course, and what I wanted to do then was to look forward a bit and see what I can glean from these equations of the second and higher orders, because I'll be curious how he'll relate those to the equations after he discusses the equations of higher degree, where it's in a higher power of the derivative, that and he in their geometric attachments like the locus. I've always been curious to learn more about the locus, the tac locus. This is a term that's new to me. I'm curious about this. But then we get into this page 61 where he discusses equations of the second and higher orders. This involves y prime prime and up into the higher and unboundedly many orders. When we turn to equations of higher order than the first, we discover that there exist certain well-defined types which admit of transformations whereby the order may be lowered. This is something that's kind of come up in the nonlinear electromechanical effects and applications, where the higher order terms that these nonlinear contributions end up having this via numerical methods or via a description of what's held constant or implicit, the method of the implicit, these reformulations or parameterizing a thing as its own differential term, that it changes in its own case, that there are various setups about how this parameterization changes, or that a numerical method is applied and the initial terms are kept in or left out, lowering the order, thus that it makes a more tractable, fungible, sensible solution for a lower order system that reflects when it's projected and pumped back up to a higher order. We discover that there exist certain well-defined types which admit of transformations whereby the order may be lowered. In particular, there are equations that may be reduced by a transformation of the dependent variable to allied equations of the first order if the latter can be integrated. A reversal of the transformation, which usually amounts to one or more quadratures, will lead to the general integral of the former. There is one small point that may be noted in passing, namely that whereas in an equation of the first order, e.g. p dx plus q dy equals 0, there is no natural discrimination between the variables. In equations where second and higher derivatives of one variable y with respect to the other x occur, the distinction is evident. This is indicating that the variables with respect to the when they have higher order partials, that in the ordinary, that they're kind of, in this sense, a sole parameter. That these variables reflect that there's the notion of the Cartesian and that they're regions, but then there's also a notion about this, essentially about this very virial approach, the variational techniques, the perturbations of the hypothesis of small perturbations, that because the orthogonal is fundamental, and that the virial, or is about the expanding of a region, is only in the extreme the fundamental, that they're each opposite theories that combine the same theory, and they have this milieu in the middle, the inductive impasse. This is just expressing that the author is so detailing that in this sense, that's my reading of it, it's one parameter, variable, and about the limits of the methods of what results when it's considered only taking a segment or a line out of the surface, what that trades for tractability. Okay. In particular, there are equations that may be reduced, if the latter can be integrated, will lead to the general integral. There's one small point that may be noted in passing, namely that whereas in an equation of the first order, e.g. p dx plus q dy equals 0, there's no natural discrimination between the variables. In equations where second and higher derivatives of one variable y with respect to the other x occur, the distinction is evident. In equations that arise from problems in physics and mechanics in particular, this distinction arises from a difference in the character of the variable, as when one represents a length and the other represents time. When, for example, they're all parameterized by time. And that length, for example, only represents an areal quantity or volumetric quantity, an inner product of some scalar with length. These are the kinds of things that get into the whole dialectic of the objects of the mathematics and the objects of the geometry vis-a-vis what is a classical function and how is that so sensible, fungible, and tractable? What are the coordinate settings and why is that so sensible and fungible and tractable? What is the means of the spiral space Fulling curve or an Archimedean spiral? Why is that so opposite, not included in classical constructions, but that the Archimedean spiral is basically the third tool of classical constructions that makes it possible that with a compass and an edge and an Archimedean spiral, that all sorts of things, or many constructions, aren't quite classical. Ever, a second breakfast. In equations that arise from problems in physics and mechanics in particular, this distinction arises from a difference in the character of the variable, as when one represents a length and the other represents time. We shall deal mainly with equations of the second order and shall consider, in particular, those classes in which a change of dependent variable enables a reduction to the first order to be effected. No general discussion of higher orders will be attempted, but when the scope of any process extends beyond the second order, the fact will be mentioned. And so this kind of goes back to the setup of the idea of CIMFT, the class of infinitely differentiable curves, which go to usually about to 0 or so, I suppose. Of all the higher orders, usually with respect to time, that our names for these are displacement, velocity, acceleration, and all the higher orders of velocity. That at the same time is as those come down from that it goes from an impulse where the impulse is underdefined as that the impulse is the direction vis-a-vis that anything is omnidirectional or it's unidirectional. So this is the uni-omni distinction, or the omni-uni distinction of sort, where it's simply so that the author is describing that according to this milieu of what's all this wonderful, sensible, fungible, and tractable means of methods, according to these definitions, that there are other things that are intractable, yet are still perfectly classical, for example, according to geometry. Classical geometry. These are the kinds of things that result why there are classical constructions and all sorts of methods that, for those in the know, can take what's a totally intractable problem, like modular forms or elliptic curves, solve them quite directly. The author's here explaining that there's these higher order contributions that exist. And then for what we saw and how things are set up to be tractable to classical and simple formulas, which is great, he's helping establishing that there's this omni for the uni. And that we have a linear narrative, we have a linear curriculum, we're able to solve these things as via means of tangents and all these things from classical geometry. And they're great, it's perfect. And that there's also a more complete side which can help us balance our understanding. That they're not that they're interchangeable, not that they can be put on the same plate and go together in terms of keeping all the plates spinning, as it were. But still, at least the author doesn't say, that we live in a flat earth and so now everything's simplified. He's just saying, as far as we can tell, as far as we can see, all the way to the horizon, it's flat. And so when I point to the horizon, I will also comment that the world is not flat. Though space-time is flat. or that the cosmological constant is a mathematical infinitesimal, which it is. We shall deal mainly with equations of the second order and shall consider in particular those classes in which a change of dependent variable enables a reduction to the first order to be effected. He's parameterizing the variable. He's describing a path, or what course the path might take. No general discussion of higher orders will be attempted, but when the scope of any process extends beyond the second order, the fact will be mentioned. In the second order, in a sense, there's up to 2 and everything beyond 2. Just like there's up to 1 and then everything beyond 1, because powers of values between 0 and 1 go to 0, and there's the triangle, isosceles triangle with 2 sides of length 1 has the other side of length root 2, but otherwise it fits in 1. All this things to do with unity and monism and the unit. Why there's what's from 0, there's what's less than 1 up to 1, then there's what's less than 0 up to 2, and then there's how 2 basically reflects splitting 0 and 1. So the interval -1 and 1 are strongly related to the interval 0, 2, with 1 in the middle. -1 and 1 has 0 in the middle. 0, 1, 2 has 1 in the middle. So that's one reason why it's different, that some of these things that then are just in the square have all sorts of classical solutions and means and milieus, or the quadrature, that make it so that stuff's closed underneath. It's not so necessarily what makes for a higher order. But as soon as you get to 3 in these higher orders, it establishes this whole other geometrical case. It's the hyper to these things. It's the hyper. And so that's just to say that that's not really so to be drawn from this treatise about why, when we have, for example, the sequence of all the binary values, 0 and 1, how that is actually any different than trinary values, is that it is. And then later there's talk about what's called Ramsey theory, and the quasi-invariant in measure theory and Ramsey theory, and the formulas that were empirical that came up that helped explain that, and thus the Ramsey theory that developed to help explain that, is that there is a difference between a system of numbers that's 0 and 1, for example, like true and false, or complements that are closed, and the modular above 3, radix 3. And so that's so in Ramsey theory, it's a thing. And so here it's also like when we talk about Ruffini-Abel, and that you can find solutions for cubics. You can find solutions for cubics. You can find solutions for quadratics. You can find solutions for cubics. You can find solutions for quartics. In the 4th degree, the 4th rank, you're at polynomials. But they're not necessarily solutions in quintics. It's a similar type of thing, representing how we can figure out whether, when we have conjectures, whether sequences of integers are finite or infinite, or or conjectures about the finitude or infinitude of objects with certain properties, that it gets into these representations also, which in another sense, the algebraic sense, are erased. That it is so that there is possible then to start talking about why it's different to have representations only in binary and then representations in higher orders. And then this is framed and built in terms of numerical resources about fundamental resources that these numbers are. And then the fundamental resources that the acts of drawing the compass, or of putting pencil to paper, or line drawing, and what result in classical constructions from the tools of geometry, which are finite and which are maintain form and proportion and . So that's, again, more about this omni and uni, that there's this uni and die. And so these are the two things that kind of we get into interesting notions of resources and numerical resources for the resources in construction, which results sensibility, fungibility, and tractability. Now I've gone quite on, but the most general differential equation of the second order in which x is independent and y dependent variable can be written fxy, y prime, y double prime equals 0. If it may be derived from an equation fxy, c underscore 1 equals 0, in which c1 are arbitrary constants, by differentiating twice with respect to x and eliminating these two constants, is known as 28.2 is known as its primitive. The elimination of c and c1 may be performed in either order, but can only lead to the one equation. For if two such equations were found, y double prime could be eliminated between them, leaving an equation of the first order having the primitive Which cannot be the case unless c and c1 are especially related. Integration consists of recovering the primitive or any equivalent expression containing two arbitrary constants, which is a general integral. And back again to the general and singular with respect to this notion and the other one. So this helps me recall some of the differences between this development, and the development that's the modern development. Because the modern development kind of takes an approach to differential analysis that gets into general methods of solutions, and particularly for some tractable systems, and about Louisville, about the Wronskian, about Lipschitz, and that these mathematicians have particular properties in this course of development. And why that is then what it does is it opens up the analysis of the solutions of these things from the closed form solutions to solutions as of according to how they may be related by transforms, and then solutions and how they may be expressed in terms of series, that then numerical methods may be applied. So it seems the difference between this text as of 80 years ago and the text of 20 years ago is that the modern text in curriculum is a bit more aligned to arrive at, within the course of a year of study or so, means of numerical methods to gain, if not closed form solutions, the numerical methods which allow then, for example, employing a computer to find solutions. Where these numerical methods courses involve, for example, on pencil and paper, hundreds of pages to crunch these numbers to do it. Whereas a computer basically has this embarrassment of riches of numerical resources in the simple algorithm of a recurrence relation that can be so defined for Newton-Raphson, that for Newton is defined pretty much the most usual thing, and Newton-Cotes is kind of like the whole differential geometry bit. And there's Runge-Kutta is another way to find the solutions to integrals and derivatives, and also in these differential equations defined by derivatives and the powers of derivatives. So that gets into why then some of this other preliminaries that are let out because of solutions in some of these solutions in the earlier treatise would be with regards to making that setup a model of a geometrical setup, and then using the tools of geometry then to make a picture of it, and then build mensuration as of by drawing the line or measuring the line. Whereas in the modern treatment, it's so designed the curriculum to provide the user with the ability to translate these systems into what become mechanically tractable in terms of computational time, and this time of the setup, what so evolves, that without this proliferation of numerical resources, the digital computer would simply have not been tractable at the time. It's fungible, it's sensible. It's fungible in the sense that, yes, anything the computer can do, you can do on pencil and paper. It's just a large amount of paper and a large amount of time. It's not tractable. Whereas what resulted in a different approach to this there is that it's more tractable. And so and then if we contrast something like solving with symmetries, that's a method to gain tractability in the symbolic, whereas the differential geometry is a means to try and gain tractability in the closed forms in its discourse on numerical methods, and ones of particular forms that some can have their order reduced to make it that they have even closed forms for some setups, and the symmetries work in closed forms when there's some constraints. That then the differential topology in quantum field theory is basically trying to explain what's going on in continuum mechanics, and all it really needs is 3 definitions of continuity, at least. So then, let's see here. I'll think for a moment on deconstructive criticism and meaning, truth, and divinity, and the lectures on physics. Here, let's see what lectures on physics has to say. The Feynman lectures on physics. Feynman, Layton, and Sands. There's that Feynman. This is volume 3. He says, what we're curious about is differential functions. Hamiltonians. The Hamiltonians are used to solve all kinds of stuff. It's a matrix. It's a Lagrangian, and so I'll be curious at how he tries to put this together. And then he talks about the ammonia molecule. Yeah, right, Feynman. Quite a character. 8.1. Two energies, the absorption of light, there's Bronquet and the Hamiltonian in the middle, and the ammonia maser. The maser is interesting in life, the microwave laser. The Hamiltonian matrix. Okay, here, let's see. How states change with time. So he's talking about the Lagrangian is parameterized by time. And the Lorentzian is the Galilean here, pretty much. But the Lagrangian is parameterized by time. The Hamiltonian matrix, 8.1, amplitudes and vectors. Before we begin the main topic of this chapter, we would like to describe a number of mathematical ideas that are used a lot in the literature of quantum mechanics. Knowing them will make it easier for you to read other books or papers on the subject. The first idea is the close mathematical resemblance between the equations of quantum mechanics and those of the scalar product of two vectors. This gets back to triangle inequality and about the path integral, as we've been talking about. You remember that if chi and phi are two states, the amplitude to start in phi and end up in chi can be written as a sum over a complete set of base states of the amplitude to go from phi into one of those base states, and then from that base state out again into chi. Bracket chi given phi equals sigma of all I of bracket x given I and bracket I comma phi. So he's describing that according to bracket, and bracket really needs to be laid out and deconstructed of the Einstein summation convention, and then it's coordinate free is coordinate based, and then it results that after triangle quantity, which is its rule, it comes down with this stuff. We explained that this in terms of a Stern-Gerlach apparatus. Stern, S-T-E-R-N, Gerlach, G-E-R-L-A-C-H. But we remind you that there's no need to have that apparatus. Equation 8.1 is a mathematical law that is just as true whether we put the filtering equipment in or not. It is not always necessary to mention that the apparatus is there. We can think of it simply as a formula for the amplitude bracket x or chi given phi. We would like to compare equation 8.1 to the formula for the dot product of two vectors b and a. If b and a are ordinary vectors in 3 dimensions, we can write the dot product this way. The sum in all I of b dot e sub I times e sub I dot a, with the understanding that the symbol e sub I stands for the 3 unit vectors in the x, y, and z directions, the orthonormal vector basis of a vector space like R3. Then b dot e sub 1 is what we ordinarily call b sub x, the partial contribution of the vector in the direction of x. B dot e sub 2 is what we ordinarily call b sub y, and so on. So equation 8.2 is equivalent to b sub x times a sub x plus b sub y times a sub y plus b sub z times a sub z, which is the dot product b dot a. So this is this inner product. It's called the scalar product. It's called the dot product. Products are just written usually with two terms next to each other, and thus it results that they're product. This is all familiar from mathematics, where we start with arithmetic. We have four symbols: plus, minus, times, divides. And so then later we just leave out x for divides, because then later x is used for a particular kind of product called the cross product. And then divides is usually written bar. You just put it over the bar or under the bar, instead of writing the divisor bar with the dots on either side, the divisor sign. Okay. And so then you can often usually write in terms of the powers of things, that when we have the exponent, you take the power, it's just the object times itself any given number of times. And when that's negative, then it's 1 over that. It's just 1 divided by that. For that 1 is this identity for how it goes and what it is. So anyways, the dot product is written this way, and it's computed that way. Comparing equations, we can see the following analogy. The states chi and phi correspond to the two vectors a and b. The base states I correspond to the special vectors e sub I, to which we refer all other vectors. This is Descartes' Cartesian coordinate, which we've been talking about, the omni and uni. The uni-coordinates. Any vector can be represented as a linear combination of the three base vectors E. A linear combination here is a sum of a scalar times each one of these. And this is the notions of linear algebra and vector spaces in this setting are very closely related. And there's much to be said for the vector space as after the establishment of the coordinate matrix and the things to do in the plane, they definitely go together. Any vector can be represented, Furthermore, if you know the coefficients of each base vector in this combination, that is its three components, you know everything about a vector. That is to say, rather, that there is an equivalent representation that is unique and distinct among all the representations of this vector form in its representation by the other form in its representation, that they have a strong intentionality that follows an extensionality, so that though they are not exactly the same, you can say you know everything about it, but really it's just that you know as much about either of them the same. But Feynman knows. In a similar way, any quantum mechanical state can be described completely by the amplitude bracket I given phi to go into the base states, and if you know these coefficients, you know everything there is to know about the state. Because of this close analogy, what we have called the state is often also called the state vector. So the state is the value, and it's basically the difference between a constant and a variable. It's the value at any given point, according to an abstract free parameterization, like when you have Kaluza-Klein and you have 5 dimensions, 3 for space, 1 for time, 1 for free, that is according to free, what is that state? Since the base vectors e sub I are all at right angles, we have the relation e sub I dot e sub j equals delta ij. The Kronecker I mentioned. This corresponds to the relations among the base states I, bracket I sub j equals delta ij. You see now why one says that the base states I are all orthogonal. That's one way to see what is orthogonal, and another thing is that like their projections don't match or meet. There's other ways to describe these same kinds of things, but when we're working off the same terms and off the same origin, it's like so. But then you always can consider that the origin is everywhere. That's what's relative is free, and so that either way you want to place the origin, that all this other stuff either works up or doesn't, in as regards to whether it's origin free for where it's coordinate free. There is one minor difference between equation ... and the dot product. We have that bracket phi given chi equals chi given phi star, but in vector algebra, a dot b equals b dot a. The dot product is a scalar. It doesn't have a sign. It's just the length. It's, I wouldn't say it's absolute so much, but it's just about. With the complex numbers, and that's arbitrary. It doesn't have direction either way. It's not like the right hand rule, having that there's a default direction after rotation. With the complex numbers of quantum mechanics, we have to keep straight the order of terms, whereas in the dot product, the order doesn't matter. This reflects the associativity, commutativity, what is not commutative, the commutators, the non-commutative, and the anti-commutative. Now we consider the following vector equation: A equals sigma of i's of ei times quantity ei dot A. It's a little unusual, but correct. It's like he's taking the outer product of the inner product. Or it's the outer product according to this arithmetic summation of terms, the additive terms, with regards to what would this inner product down from the multiplicative, as we've been talking about the difference between arithmetic and algebra. It's a little unusual, but correct. It means the same thing, disregarding this other omni concern, as A equals sigma I, A sub I E sub I equals AX EX plus AY EY plus AZ EZ. So he's writing this transformation rule and showing how this transformation rule is reversible and symmetric and reflexive. Notice though that the equation 8.6 involves a quantity which is different from a dot product. A dot product is just a number, whereas 8.6 is a vector operation. So when we have the notions of when the scalar value has a natural representation as a vector, it's embeddable in the vector space, the one-dimensional vector space. And so sometimes we think of types like the integers and then the rationals as a closure of those to division, and then the reals as a closure of those after the definition of the axiom of the least upper bound. But similarly, it's just that some of the real numbers exist first, and irrationals are the ones defined by integers. So here what Feynman is just pointing out is that these two different representations, according to a strong theory of types, has that there are types according to these the way that the relations hold up over the operator calculus about these things, of their values, and the representations of their values, that this is a thing. Well, today we talked a little bit about stuff like the higher order and unbounded and differential equations, and coming up into why we have these many subfields of differential analysis, and because differential equations basically reflect a formulation of all matters of change. There was talked about, what are setups? Can you really write everything as somehow an equation or formula? And if so, then how do we arrive at solutions with these things? And it was talked about the differences between the curriculum and the narrative of the objects and the definitions, because there was a time where it was necessary that it resulted that the sensibility first and fungibility and tractability resulted up in accordance with the tools of the symbolic and the knowing some methods and gleaning those other aspects of the setup to apply these methods that otherwise today the setup is along the lines of a general course towards providing a rich means of establishing the distinctness and uniqueness of solutions and then crunching them. That also then for differential geometry, we have these idea of the submersions, which are also going to reduce to these linearizations that make it so that some have closed forms, so they can be computed exactly, and be careful with using the word exact. Similarly with the symmetries and these other methods, these are ways to apply greater topoi to the thing, the topologies, toposes, topoi, to those things that result that's why we want to have this corralling of them together. And then it gets back to topology, and then the definitions, as we talked about the omni and uni, and then what choices we make for tractability that results so that it's suitable to make this kind of thing a linear curriculum, so that in the course of development we have a sufficient context for intuition to arrive at means, to see the way, to draw the line. Well, all right then. I hope this finds you in good spirits and health, and you and yours, and so on. Good day.